Welcome students to this next session in the subject of industrial metallurgy. We are discussing iron carbon systems. This is session number 41, and in this session we would show that each type of steel, the classification that we have done on the basis of eutectoid reaction, hypoeutectoid steels, then eutectoid steel, and then the hypereutectoid steels. What type of microstructure development takes place in them as they are cooled from a very high temperature down till the room temperature under under equilibrium conditions. So we have already discussed, but just for your reference, I'll again repeat what are the different types of steels on metallurgical basis, and also then we'll see the equilibrium cooling of the metallurgically most simple steel, that is eutectoid steel. Then we'll go on to see it for a hypoeutectoid steel, and finally for a hypereutectoid steel. So let's get started. Again, for your reference here, the iron cementite diagram has been shown. And in this iron cementite diagram, you can see this is the way how we have classified our steels. This composition represents the eutectoid steel. All steels to the right are hypereutectoid steels. All steels to the left are hypoeutectoid steels. Essentially, under equilibrium conditions, the room temperature microstructure of eutectoid steel consists only of perlite. That of hypoeutectoid steels would consist of perlite plus proeutectoid or primary ferrite, and that of hypereutectoid steels would consist of perlite along with some proeutectoid cementite. Okay, students, so first of all, let's start with the equilibrium cooling of a 0.77% carbon steel, which we call as the eutectoid steel. Now, as we have been doing in the past, the alloy in which our interest lies, we mark that composition. This is 0.77, and we draw a vertical line. And now the difference is that earlier we used to take this vertical line and start discussion on the equilibrium cooling for an alloy when the alloy was above its liquidus in the molten state. But now there is no need. See, our interest lies in that how we would improve upon the properties of steel, and especially through heat treatment. And minded, when we do heat treatment, we reheat the steel from room temperature till the steel attains a fully austenitic state or a partially austenitic state. We will never go to a temperature beyond the austenitic region. So whenever somebody asks you to elaborate on the microstructure evolution in any type of steels, the best is to, the highest temperature that you need to take is when the steel is in the austenitic region. So I have taken steel at a temperature corresponding to point P, then I'll start slowly cooling it, and down till the room temperature I'll discuss with you as to what type of microstructural changes will take place in the steel after it had this austenitic state. So at point P, we have taken this eutectoid steel, and this eutectoid steel's microstructure at point P is this, contains 100% austenite, 100% by weight austenite. And what's the chemical composition of austenite? Because it's the only phase present in the steel, the chemical composition of this phase has to be the same as is the composition of the steel in which it is present. Okay, then we start cooling the steel under strict conditions of equilibrium. No change would occur in the steel even at point R. The same microstructure exists even till eutectoid temperature. There exists no change in the microstructure of the steel. But as the steel reaches the eutectoid temperature, that is corresponding to point K, you would realize that we have austenite of 0.77% carbon present in the steel and is present at the eutectoid temperature. Both the things that are required for the eutectoid temperature are there. The austenite would convert into 100% perlitic structure. So this entire austenite that was there in the steel converts to 100% perlite, and in that 100% perlite, you see 88.82 percentage is ferrite, and remaining 11.18 percentage is cementite. if somebody wants to exactly find out this, what he has to do is, this is a eutectoid steel, 0.77% carbon, just at a fraction below point K, the eutectoid reaction would have occurred. Now use M, K, and this point as the tie line, and you can find out the amount of ferrite and cementite in it. All ferrite and cementite that is present in the steel is eutectoid ferrite and eutectoid cementite. You will find out that ferrite is about 88.82%, cementite is about 11.18%, and that reiterates our earlier point that in the pearlitic structure, ferrite is to cementite amount ratio, mass ratio is 8:1. Their densities being the same, their volume ratio is also 1. So we generally show ferrite lamella about 8 times in width as compared to the cementite lamella. Students, even when the steel now is cooled to lower temperatures down till the room temperature, there would not be any change in the microstructure of the steel. Yes, when we'll take up this matter in more detail in our live classes, I will definitely discuss with you the significance of this line. And the significance of this line is that it tells us about the change in the solid solubility of carbon in alpha solid solution with decrease in temperature. So the ferrite that you get over here is of 0.02% carbon, but as the steel lowers down to a comes down to a lower temperature, ferrite present in the steel cannot accommodate 0.02% of carbon, and ferrite pushes that excess of carbon out of it again in the form of cementite. So what would happen if in this eutectoid steel somewhere over here, if you had all eutectoid ferrite and cementite, and ferrite was of maximum carbon 0.02, when you come to room temperature, some ferrite, the carbon solubility of ferrite has decreased from 0.02 to 0.0008% carbon, and this carbon that has come out of ferrite comes out in the form of cementite. So what you see is that some more amount of cementite gets formed, but students, the amount of this additional cementite that gets formed because of precipitation of carbon out of ferrite is so small that it is insignificant in amount, and we do not show any changes happening to the microstructure practically. Okay, then we move on to the equilibrium cooling and the microstructure evolution in hypoeutectoid steels. Now, to explain the case of a hypoeutectoid steel, I have taken a steel which contains 0.38% carbon. All balance is iron. Again, we draw a vertical line such that we take this at a high temperature at point Q. When it is in a complete austenitic stain, the steel contains only austenite in it of 0.38% carbon, 100% by weight. So at point Q, you can see the microstructure of the steel is this. We start cooling the steel, and no change would occur in the microstructure of the steel till we have reached point R. Point R is the point where austenite will start precipitating carbon out of it, and it would precipitate it out in the form of ferrite. So you will realize that when your steel gets onto a temperature corresponding to point R or anywhere below it, now austenite has precipitated some carbon out of it in the form of ferrite. So now you are in the ferrite plus austenite region. There are two phases in your steel now rather than only austenite. And somewhere over point T, if I want to show you the microstructure has been shown over here. You'll still have austenite 68.52, but with different amount of carbon. Here it was of 0.38% carbon. Now somebody can wonder, sir, how, if it has precipitated carbon out of it, how has its carbon amount increased? But you please realize here 0.38% carbon composition was of 100% austenite. Here the amount is considerably less, and in that considerably less, this carbon composition appears to be large. The total carbon is the same and is spread across austenite and this ferrite. And this ferrite, as you now realize, is the ferrite which is present in the steel before the eutectoid reaction. And so this is being referred to as pro-eutectoid ferrite. So at point T, the microstructure comprises of austenite. This is the chemical composition. This is the line that I have used, and I have marked all these points W, S, X in this diagram, and WX, whatsoever has been written in the microstructures, the composition can be picked, like W is 0.01 carbon. See, here is W, this is 0.02. So this has been taken as 0.01. So then when you are just on the verge of reaching the eutectoid temperature, here in this diagram that represents point K, slightly above it, you will have the maximum amount of pro-eutectoid ferrite that could have got formed in this steel. And the same we are trying to show, remaining would be austenite. And this temperature, at this temperature, slightly above the eutectoid temperature, it's always important to show the microstructure, but because we should know what is the amount of austenite which would now actually transform to pearlite through the eutectoid reaction. So when you see over here, slightly above the eutectoid temperature at point K, we have pro-eutectoid ferrite, and this is of maximum carbon. Students, another very interesting fact. This is now 52%. So, and austenite is 48%. And this is how I've picked up the chemical composition. So just after the just as the temperature drops a fraction below and the eutectoid temperature is reached, the eutectoid reaction occurs, and all this 48% austenite transforms to 48% pearlite. So now if we look at the microstructure slightly below the eutectoid temperature, the microstructure, the only change that you will see is that this austenitic region has transformed to pearlitic region. So now you can see three different things. One is this eutectoid ferrite, the other is this eutectoid cementite, and the third is this pro-eutectoid ferrite. But the phases are only two. The phase is ferrite and cementite. But specifically, you would say, sir, we have pearlite and pro-eutectoid ferrite in the microstructure, and you can even individually find out that what's the total amount, because the difference is that the source of cementite is only one, eutectoid reaction, but the source of ferrite has been two. It has come through simple solidification in this region, and it has also come through isothermal reaction, eutectoid reaction at this temperature, and the same has been shown over here. Now, as you move from a point just below the eutectoid temperature to the room temperature, or slightly above the room temperature, the noticeable change is that alpha is not now of 0.02 carbon. Because of this line, alpha, because of the solvus lines, alpha is continuously showing a decrease in carbon, and at point V, or somewhere close to the room temperature, you will see that the ferrite that is present in the steel is not of this maximum carbon, rather of a very, very small amount of carbon, though amount is the same. Why amount is the same? Because the precipitation of carbon from this an amount to this an amount leads to very small amount of formation of cementite. So cementite cementite, students, will always be of 6.67% carbon. That does not change because it's a compound. Yes, the amount of cementite has slightly increased from 5.41 to 5.69. So that's all about the equilibrium cooling of hypoeutectoid steel of 0.68% carbon. Exactly similar changes would take place if you take any other hypoeutectoid steel. Now I come to the equilibrium cooling of a hypereutectoid steel. The only big difference between the equilibrium cooling of a hypereutectoid steel is that cementite phase has got this. See, in case of a hypereutectoid steel, rather than this pro-eutectoid ferrite, pro-eutectoid cementite will get formed. And this pro-eutectoid cementite has got a bad habit that if it is depositing in the presence of a solid solution, see, ferrite here was depositing in the presence of austenite, which is a solid solution. So if cementite is precipitating in the presence of a solid solution, and that too by slow cooling, it always deposits itself in the form of a brittle network on the grain boundaries. So like here you are seeing this pro-eutectoid ferrite in the form of dendrites or lumps in between the grains. The same would not happen in case of hypereutectoid steels, because there, instead of this pro-eutectoid ferrite, you have pro-eutectoid cementite, and pro-eutectoid cementite, whenever it deposits itself due to slow cooling, and we are discussing equilibrium cooling, slow cooling, it always deposits itself on the grain boundaries. So let me make this point clear. To show the equilibrium cooling of a hypereutectoid steel, we have taken a hypereutectoid steel which is containing 1.35% carbon in it, knowing that anything beyond 0.77 is a hypereutectoid steel. We draw a big line over here, vertical line. We start at temperature Q when my steel was in the austenitic state. There is only one phase in it. The chemical composition of that phase would be 1.35% carbon. Weight would be 100%. No change would occur till I've reached point R. No sooner I take my system to temperature R, the material system is bound to come into a two-phase region, means austenite will start precipitating cementite into it. So somewhere at point S, if I show you the microstructure, see here austenite 1.3. Now as we come to point R, this is the tie line or the lever which we are using to find out the amounts and the composition. You see austenite is of 0.88% carbon, cementite is always of 6.67% carbon, and austenite is 91.88. Remaining has now become cementite, but cementite, as I discussed, is coming on the grain boundaries. As cooling will proceed and you reach a temperature slightly above the eutectoid temperature, maximum amount of this pro-eutectoid cementite would be seen, and its amount has increased from 8 to 9.83%. So just after the eutectoid reaction, all austenite will transform to this lamellar perlite, and this pro-eutectoid cementite remains as such. And now when you move from eutectoid temperature to about room temperature, the only big change is that this ferrite, which was present in perlite, was of maximum solid solubility 0.02% carbon. Its solid solubility decreases and it becomes of 0.008% carbon, and slight amount of cementite would have increased. So if here cementite was say 20.11, here it has become 20.23, but that 20 point something is shown has to be found out within the perlite. So students, this brings us to the end of equilibrium cooling of each type of metallurgical, each type of steel on the basis of metallurgical classification. I hope you have understood all the things. Thank you so much for watching.